Hey everyone, this is going to be the solution set for the quiz on June 17th. Alright, let's see if I can get my camera to focus. There we go. Alright, so problem 1A. We have a 0.280 kilogram volleyball. I swear I can spell volleyball. And it is approaching a player horizontally at an initial speed of 15 meters per second. The player hits it with their fist in the opposite direction and sends it off with a speed of 22 meters per second. So first off, the thing to note is that one of these has to have a negative sign on it because the volleyball changed direction. So if we imagine, here's our volleyball player, and the volleyball comes from the right, then let's add the negative sign to our initial speed, because that way the volleyball will be going back to the right after it's been hit. Okay, so we want to find the impulse delivered to the ball by the player. Well, impulse is just the change in momentum. So mvf minus mvi. We can pull out a factor of m, and then we just have vf minus vi. The mass of the volleyball is 0.280 kilograms. And the change in velocity is going to be 22 meters per second minus negative 15 meters per second. It's very important to take into account the fact that the ball is changing direction rather than just accelerating in the same direction. And that's what that negative sign is for. Then, the impulse delivered to the ball is 10.4 kilogram meters per second. All right, I guess I'll keep going with part B, since it's technically part of the same problem. All right, 1B. So the player's fist is in contact with the ball for 60 milliseconds. Oops, 60 milliseconds, not meters per second. Or in other words, 0.0600 seconds. And we want to find the average force exerted on the ball by the player. Well, we find average force by taking our impulse, or more properly, our change in momentum, and multiplying it by, or dividing it by, the time it took for that to happen. Because force is not just mass times acceleration, it can also be thought of as a change in momentum divided by a change in time. So we already found our change in momentum to be 10.4 kilogram meters per second, and we know that it took 0.0600 seconds for that interaction to happen. So then the force delivered to the ball is going to be 173 newtons. All right, number 2. This is a conservation of momentum question. We have a bullet with a mass of 8 grams, or 0.00800 kilograms, which we need to use. And it's fired into a block of wood that has a mass of 9 kilograms. So we'll call that M2, 9 kilograms. And the block is not restrained in any way. After the impact, it has a horizontal velocity of 40 centimeters per second. Or 0.400 meters per second. Now, if we take the initial velocity of the block to be 0, which makes sense, the block is at rest before it has a bullet fired into it, we can write down conservation of momentum and use that to find the velocity of the bullet. So Pi equals Pf. This is essentially a perfectly inelastic collision. Pi equals Pf. The initial momentum is just that of the bullet. So m1 times v1i. And then the final momentum is going to be the combined mass of the block and the bullet times the velocity of the block-bullet system. So we know all of these things except for V1I, so let's solve for V1I. So we get the sum of m1 and m2 times the final velocity divided by the initial mass, or the mass of the bullet. So plugging everything in, we get 0.00800 kilograms, which is the mass of the bullet, plus the mass of the block, which is 9 kilograms, times the final velocity, which we found to be 0.4, or which is given to be 0.4 meters per second. And all that is divided by the initial mass of the bullet. And when we do all that math out, we find that the initial velocity of the bullet is about 450 meters per second. So that's just a pretty straightforward conservation of momentum in a perfectly inelastic collision type of problem. All right, here's the solution for number 3. Let's start with 3A. Okay, so first, before I do anything else, I have to note there's actually a typo on this that basically made 3B impossible to do because it's a contradiction. So I said perfectly inelastic, and I meant perfectly elastic. I don't know how that got through the proofreading, but I will grade this one accordingly. So either I'll just give everybody full credit, or I'll give everybody full credit if they try to do it either way. But for the record, I actually meant perfectly elastic on 3A. Okay, with that in mind, let's actually go through the problem. But I'm going to treat it as though what I said was what I meant. So I'll treat this as you would an actual elastic collision. Okay, so we have a neutron traveling at 8.8 kilometers per second. So let's write down the mass and velocity of the neutron. So the neutron has a mass of 1.67 times 10 to the minus 27 kilograms. And it has an initial velocity of 8.8 kilometers per second. And let's just convert that quick to meters per second, because that's what we're going to be using in the actual calculation. So that's 8,800 meters per second. Okay. Then it collides with a deuterium. Deuterium is heavy hydrogen, means that regular hydrogen has a nucleus that's just a proton, whereas deuterium has a nucleus that's a proton and a neutron. So deuterium collides with deuterium at rest. So the mass of the deuterium nucleus is 3.34 times 10 to the minus 27 kilograms. And its initial velocity, because it's at rest, is just 0. Okay, so this is, again, we're going to treat this as I meant it, not as I actually wrote it. We're going to treat it as a perfectly elastic interaction. And what that means is that both momentum and energy are conserved. So let's write down conservation of momentum. Mn Vni equals Mn Vnf plus Md Vdf. Okay. Remember, the initial velocity of the deuteron, or the deuterium nucleus, is 0, so there's no momentum from that at the beginning. So that's one of the equations we need to solve, and we can solve this. We can solve this for VNF and VDF like this. You know what? I'm going to leave it in this form for now. Then conservation of energy gives us, remember, our conservation of energy equation for elastic collisions is actually very simple. We actually simplify it down from 1/2 mvi squared, etc. Conservation of energy can be simplified to this. And since the deuteron is at rest at first, that term goes away and we get VNI equals negative VNF minus, you know what, I'm just going to carry this negative sign through. So we have VDF minus VNF. Okay. And that's equal to VNI. Okay, so these are the two equations that we actually need to solve in order to get, in order to work out the velocities. So let's write these a little more simplified. I'm going to suppress sig figs and units for now, like I do in a lot of problems, just to make things a little clearer. So let's see. Let's just multiply mass of the neutron times its velocity. Okay, so the initial momentum is 1.47 times 10 to the minus 23. Oops. Kilogram meters per second. And that's going to be equal to, we'll write this a little bit differently. We'll write this as, actually, you know what? I'm just going to plug in the numbers. 1.67 times 10 to the minus 27 kilograms times VNF, one of the things we need to find, plus 3.34 times 10 to the minus 27 kilograms times VDF. Conservation of energy gives us, let's see, we have initial velocity, so I'll write this a little more carefully. 8.80 times 10 to the third meters per second equals, oh, right, I said I would get rid of sig figs and units, so I'll just do that. 8800 equals VDF minus VNF. So we have a system of two equations here, and we need to solve for two unknowns, so we can do that. So let's solve for, doesn't really matter which. It's slightly easier to solve for VDF here, so I'll do that. VDF equals 8800 plus VNF. Now we have an expression for VDF, so let's plug that in here. So that gives us 1.47 times 10 to the minus 3, or I'm sorry, 23 kilogram meters per second equals 1.67 times 10 to the minus 27 kilograms times VNF plus 3.34 times 10 to the minus 27 kilograms times 8800 plus VNF. So we've reduced this equation here from two variables, VNF and VDF, into one variable. So then let's see, let's multiply that out. I'm going to do a little bit of algebraic reduction here just so it looks a little, right, I said I'd leave out units. I'm going to leave out the units. So it looks a little nicer. Okay, so we have 1.47 times 10 to the minus 23 equals 1.67 times 10 to the minus 27 times VNF plus 2.94 times 10 to the minus 23 plus 3.34 times 10 to the minus 27 times VNF. So we just have a bunch of numbers here and one variable, so we can solve this for VNF. So VNF is going to be, let's see, going to be negative 1.47 times 10 to the minus 23 kilograms over, kilogram meters per second, over 5.01 times 10 to the minus 27 kilograms. And that leads to a final velocity of negative 2930 meters per second, or negative 2.93 kilometers per second. So crashing into the deuteron means that the neutron has actually reversed its velocity. If the neutron's coming in from the left, it'll bounce back, it'll rebound back off the deuteron with a velocity of 2930 meters per second. So we found the velocity of the neutron. We can now find the velocity of the deuteron from this equation here. So the velocity of the deuteron is just 8,800 plus the velocity of the neutron. So that's 8,800 minus 2930. And that should give us a velocity, sorry, just a second. Okay, that should give us a velocity of 5,870 meters per second. Okay. So just to summarize, the neutron comes in, hits the deuteron at rest, and then the neutron rebounds back to the direction it came from at 2930 meters per second. And the deuteron is now traveling to the right at 5,870 meters per second. And we were able to get that using conservation of energy and conservation of momentum. So for a perfectly elastic collision, you need to use both conservation of momentum and conservation of energy in order to work out the velocities of the interacting bodies. Okay, so that's 3A. Now here's 3B. Due to my typo on the quiz, you actually couldn't do this if you followed exactly what I said, because remember, perfectly inelastic collisions don't conserve energy. So this is kind of nonsense. But we'll do it as though I actually wrote what I meant on the quiz. So we need to show by direct calculation that energy is conserved in this collision. So we really just need to calculate kinetic energies before and after. So the initial kinetic energy, write that as Ki, is just going to be 1/2 times the mass of the neutron times its initial velocity squared. All of those we already know. So it's going to be 1/2 times 1.67 times 10 to the minus 27 kilograms times its initial velocity of 8.80 times 10 to the third meters per second. And remember, we need to square the velocity. So that's going to be despite the fact that velocity is large and going to be squared, it's still going to be a very small number in terms of energy. And so I find that the kinetic energy, the initial kinetic energy, and what we hope will be the final kinetic energy, if kinetic energy is conserved, which it should be, is 6.47 times 10 to the minus 20 joules. So that's the initial kinetic energy. So let's now check the final kinetic energy. Now, because we have two objects moving, we need to have two versions of 1/2 mv squared, one for the neutron after it's rebounded off the deuteron, and one for the deuteron after it's been forced into moving by the neutron. So we're going to have 1/2 mn vn f squared plus 1/2 md v sub d f squared. Let's pull out that factor of 1/2, and then we have our neutron mass times the final velocity of the neutron, which remember we found to be negative 2930 meters per second. And then we'll have the mass of the deuteron, 3.34 times 10 to the minus 27 kilograms, times its speed after the interaction, which I believe we found to be, what do we get? Where are my papers? Ah, right, okay. 5870 meters per second. Okay, so let's calculate that out and see what we get. And I get back out what I expected to, 6.47 times 10 to the minus 20 joules. So since EI equals EF, energy is indeed conserved. Okay, so now just a quick note on what you would have gotten if you had done this the way I wrote it. So if we treat this as a perfectly inelastic collision, then the basically the neutron will be absorbed by the deuteron into what's called tritium, actually, which is hydrogen with 2 neutrons. So let's do this quickly as written. So then so energy isn't conserved in this collision because it's perfectly inelastic. Okay, momentum conserved, energy is not. So let's write down the momentum for this. Pi equals Pf, so we have Mn Vni equals Mn plus Md times the final velocity of whatever it is that they're moving together. Because remember, in a perfectly inelastic collision, the neutron will slam into the deuteron and actually combine with it. And then they'll move together afterwards. So then if you had done it this way, your final velocity would be m sub n v sub ni over the sum of their masses. And we can do that quickly. Mass of the neutron is again 1.67 times 10 to the minus 27 kilograms. Its initial velocity was 8,800 meters per second. And then the sum of their masses we found to be 5.01 times 10 to the minus 27 kilograms. So plugging everything in there. We find that the system will move off to the right at 2930 meters per second. And 3b is nonsense. Energy isn't conserved. All right, so when I grade this, I will either accept, if you kind of grokked what I actually meant, which is a perfectly elastic collision, obviously you get full credit for that, but if you also did this and said, okay, all right, I can do perfectly inelastic, but I can't conserve energy, what happened? That's also acceptable, and you won't lose points for that. That was my mistake. Okay, so that's it for quiz number 6, I think this was, the one on June 17th.